Hi Year 13, Mr. Vinord here. Today we're going to work through how to write the electron configuration of atoms. Now you may remember from year 12, looking at the chlorine atom for example, chlorine has the atomic number of 17 on the periodic table. That tells us that chlorine has 17 protons. Because atoms are electrically neutral, the positives and negatives have to be equal. So if there's 17 protons, there also have to be 17 electrons. If we wanted to write the electron configuration for those 17 electrons, well, we know the structure of the electron shells, where the first can hold 2, the second can hold 8, the third can hold 8, etc. So we would write the electron configuration for chlorine as being 2 in the first shell, 8 in the second shell, and 7 in the third. The first shell can hold 2 maximum, the second shell can hold 8 maximum, the third shell can hold 8 maximum, the fourth shell can hold the rest, is what we would say previously. But for chlorine, because we just have 17, 2 in the first, then it's full, 8 in the second, then it's full, and the remaining 7 going in the third. What we're going to look at in this video is how to give a lot more detail about the precise location of those electrons. Here we're just saying which electrons are in which energy level. We can actually go a lot more in depth and say what sub-level are they in, and even which orbital are they in within a sub-level. So what the electron configuration for chlorine looks like using this method is this: 1s2, 2s2, 2p6, 3s2, 3p5. That looks pretty intense, and it's a big jump to go from there to there, but we're going to work through the steps and we're going to explain what the energy levels, sub-levels and orbitals are, and hopefully by the end of this video you can get to this step yourself as well. So let's have a bit of a go. First of all, we're starting at the bottom of the page here. What we've typically dealt with in the past are what we call the main energy levels. So we would say the first main energy level holds 2, the second holds 8, the third holds 8, etc. What we're adding on now is that the energy levels are made up of sub-levels. The number that each energy level can hold, the number of sub-levels it can hold, depends on how high the energy level is. I'll explain more on that later. Sub-levels contain orbitals. The number of orbitals that each sub-level holds depends on the type of sub-level, whether it's an S, a P, a D, or an F sub-level. Each different type of sub-level holds a different number of orbitals. And an orbital is simply a region of space where an electron is likely to be found, and one orbital can hold a maximum of 2 electrons. So summary, an orbital, being a region of space where electrons are likely to be found, can hold 2 electrons. Those 2 electrons spin in opposite directions. A sublevel is made up of orbitals, so it contains maybe one, maybe more orbitals, depending on the sublevel type, S, P, D, or F. Those are the 4 sublevel types that we're going to look at. And the main energy level is made up of sublevels, so these S, P, D, F sublevels, which are made up of orbitals. And the number of sublevels depends on how high the energy level is. So first of all, we're going to look at the sublevels, and then we're going to look at the energy levels. We don't need to look at the orbitals anymore, because just remember, an orbital can hold a maximum of 2 electrons. So this table is going to hopefully explain nice and clearly how many electrons each sublevel can hold. The 4 sublevels, remember, are S, P, D, and F. The S sublevel is the first sublevel, and the S sublevel has 1 orbital. If an orbital holds a maximum of 2 electrons, hopefully you can guess that the maximum number of electrons an S sublevel can hold is 2. 1 times 2 is 2. A P sublevel holds 3 orbitals. If each orbital holds 2 electrons maximum, then those 3 orbitals can hold 6 electrons maximum. A D sublevel holds 5 orbitals. Each orbital holds 2 electrons maximum, so the 5 orbitals combined can contain 10 electrons maximum. And the F sublevel can hold 7 orbitals, each orbital holding 2 to give a total of 14 electrons. So you'll notice a couple of patterns there. As we go up the sublevels, the number of orbitals increases by 2 each time, and the total number of electrons held increases by 4 each time. That can be quite helpful for remembering how many orbitals and electrons go in each sublevel. Now let's look at how many sublevels and what sublevels are in each energy level. In the first energy level, there is only one sublevel, and it's an S sublevel. In the second energy level, there are two sublevels, an S and a P. In the third energy level, have a guess, 3 sublevels, an S, a P, and a D. In the fourth energy level, have a guess, yep, you got it, 4 energy levels, an S, a P, a D, and an F. So in the first energy level, we have an S subshell. That S subshell can hold 2 electrons maximum. So in the first energy level, we have one S subshell, which can hold a maximum of 2 electrons. 2 electrons in the first energy level. In the second energy level, we have an S subshell, which can hold 2 electrons, and a P subshell, which can hold 6 electrons. So in the second energy level, how many electrons total? 8. So again, we're noticing a bit of a pattern. 2, 8. The third and the fourth, it gets a little bit more complicated. So to explain that, we're going to go to another diagram. Here we're going to look at the order for filling electron sublevels when you are writing the electron configuration for an atom. So this diagram here tells us which order we fill them in. We fill from the lowest energy to the highest energy. So low energy to high energy. Now you would logically think that that means you would go 1, 2, 3, 4, 5 and fill them in that order. But these energy levels are written in order of distance from the nucleus. 1s2 is the closest, then 2s2, then 2p6, then 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14. That's the order in proximity in terms of distance. But we fill them in terms of energy. And so these red arrows tell us what order to fill them in terms of energy. So you start here and you follow each arrow starting from the left, moving to the bottom right there. So we fill the 1s2 first, then we fill the 2s2, then we fill the 2p6, then we fill the 3s2, then we fill the 3p6, then we fill the 4s2, then we fill the 3d10. So instead of going from 3p6 straight to 3d10, we actually go from 3p6 down to 4s2. So that's where the first sort of abnormality kicks in there. The reason being, the 4s2, even though it's further away from the nucleus than the 3d10, we fill it before the 3d10 because it is at a lower energy level due to its shape. So you follow the red arrows, and the red arrows give you the order for filling the sublevels for an electron configuration. Lots of detail. Let's work through some examples. That's the best way to tackle these problems. The 3 examples that we'll look at here are lithium, magnesium, and sulfur. Lithium has the atomic number 3. That means it has 3 protons and also 3 electrons. So the electron configuration for lithium, written the old way, would be 2, 1. Written the new way, we would say in the first energy level, there is only one subshell and it's an S. And that S subshell can hold 2 electrons. And it has 2 electrons to fill because we have 3 total. We've only used 2 of them so far. We have 1 electron still, so in the second energy level, in the S subshell, we are going to place that 1 electron. Now there are some similarities between the 2 ways of writing electron configurations. Here we can see that in the first energy level there's 2 electrons, in the second energy level there's 1 electron. 2, 1. So there are some overlap, there are some similarities, but it does get a little bit more complex as we use bigger atoms with more electrons. Magnesium has the atomic number 12. So writing its configuration the old way would be 2, 8, 2. The new way, we say we have 12 electrons. So in the first energy level, I have an S subshell, and it's going to have 2 electrons in it. It will be filled. In the second energy level, I have 2 subshells, a 2s and a 2p. The S can hold 2 electrons, and the P can hold 6 electrons. So 1s2, 2s2, 2p6. How many have I used so far? 2, 4, and 6 is 10. I still have 2 electrons to use. So I need to go to the third energy level. First of all comes the S subshell, and the S subshell will have 2 electrons in it. That's the maximum it can hold. So how many have I used? 2, 4, and 6 makes 10, and 2 makes 12. I've used all of my electrons, and what I can see from this new configuration is there are 2 electrons in the first energy level. In the second energy level, I have 2 and 6 makes 8. In the third energy level, I have 2. So 2, 8, 2. Same still applies. Sulfur has the atomic number 16. If you get it, at this point pause the video and have a go at writing the electron configuration for sulfur yourself. So for sulfur, the old way, we would write it as 2, 8, 6. The new way, we will say in the first energy level, there's an S subshell, and it can hold 2 electrons. We've used 2 out of our 16. In the second energy level, we have an S and a P. The S can hold 2, and the P can hold 6. Now we've used 10 out of our 16. Still 6 to go. So we can fill the 3s2. That leaves us with 4 remaining. And then we go to the 3p. And the 3p can only have 4 out of its 6, because there's only 4 left to use. 2, 4, and 6 makes 10, and 2 makes 12, and 4 makes 16. So that is not a full subshell. There's 3 examples. Let's look at a couple more. To make life a little bit easier for these slightly more complicated ones, I've written the order that we fill sublevels in at the top of the page there, just for us to refer to. Titanium has the atomic number 22. So let's fill titanium. First energy level, S subshell, 2 electrons. Second energy level, there's a 2s and a 2p. We can have 2 and 6 there. 2, 4, and 6 makes 10 so far out of my 22. So I go to the third energy level. 3s2, now I've used 12. 3p6, so now I've used 2, 4, and 6 makes 10, 12, 18. 4 more to go. So I look up here and I can see I've done 3p6. Now I go to the 4s2, so that's where my slight exception kicks in. Now I fill the 4s before the 3d. So I've got 4s2. How many have I used? 2, 4, and 6 makes 10, 12, 18, 20. Still 2 to go. So those 2 need to go into the 3d subshell. There will just be 2 in there. Slightly more complex, the bigger the atom gets. Let's look at nickel, which is slightly larger again, 28. So, 1s2, 2s2, 2p6. First energy level, S subshell holds 2. Second energy level, 2 subshells, S and a P, both full, 2 and 6. We've used 10 electrons there. Third energy level, S and P, 2 there, 6 there. 2, 4, 6 is 10, 12, 18. So we've used 18 so far. Still 10 to go. Now we fill the 4s. 2 can go in there. Still more to go. Go into our 3d subshell. How many need to go in there? 2, 4, 6 makes 10, 12, 18, 20. We need to use 28. So 8 will go in there. And that's the electron configuration for nickel. So you can see it's the same general idea as what you've done in the past, but it's a lot more specific. The easiest way I find is to memorize the order that you fill the electrons in, and then you just go through and count how many you've got and put them in the correct place in that sequence. 2 exceptions. In chemistry there's always exceptions. Chromium and copper. Now you've learned in the past that having a full valence shell is a stable configuration. Slight little bit of extra detail. A full subshell or a half full subshell is a stable configuration. That slightly changes the way we write the configurations for chromium and copper. Let's work this through. Chromium has the atomic number 24. So that means its electron configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How many have I used there? 2, 4, 10, 12, 18, 20. Still 4 to go. 3d4. That's what its configuration should be. But it's not. It's an exception to the rule. And what happens here is chromium, instead of taking this configuration, actually has one of its electrons in the D instead of the S. Reason being, if it moves 1 from the S to the D, it has a 4s1, which would then be a half-filled subshell. An S subshell can hold 2 electrons, so if it's only got 1, it's half-filled, and that's a stable configuration. If we move 1 up to the D subshell, it would be 3d5. And 5 out of 10 of our D electrons would also be a half-filled subshell. So instead of having a full and a neither, it's got 2 half-filled, which is stable. So chromium actually becomes 4s1, 3d5. So that's an exception. Copper's the same. Now copper is the same configuration up to a later point, so I'll just quickly write it here. This is what it should be, 4s2, 3d9, because copper has 29 electrons. Again, copper will move 1 electron from its S subshell to its D subshell to become 4s1, 3d10. So that it gets a half-filled subshell and a fully filled subshell, rather than a full and a neither. So those are the two exceptions to the electron configuration order of filling, and you need to be aware of those two exceptions. One last little tip for experts. When you get to the later, the larger electron configurations, there is a shortcut. So for example, for nickel, we earlier wrote that nickel had the configuration because it has 28 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. That's the electron configuration of nickel. Now what we can do to make this shorter, rather than writing that whole thing out every time, is we can actually say that part there, that is the electron configuration of the inert gas argon. And so what we can do is we can say, instead of writing out the whole configuration, I'm just going to say that that part there is the same as the inert gas argon, and I'm going to add on the bits after that inert gas, just to make it a little bit easier for myself. So that's a shortcut for writing the longer configurations. Now obviously use this sensibly. You don't need to put helium in here instead of writing 1s2. That's a bit ridiculous. Probably not neon either, but from sort of potassium onwards, so 19 up, I would use argon and then just say what comes after the electron configuration of argon. It just makes it a little bit quicker. So I hope you found this helpful. All the best, give it heaps. Any questions, we'll deal with those later on. Cheers.